Hello, everyone, and welcome to the June 2025 Gains Product Webinar. And I'm Amber Sally. I'm the Vice President of Industry Solutions, and I will be guiding you through our session today. So Gains has these product webinars in order to introduce new product innovations from Gains that help you enable more resilient, insight-driven decisions. And decision making and improving decision outcomes is something that we're passionate about here at Gains. Our mission is to help you make smarter decisions and drive better outcomes and helping you really understand the impact of the decisions that you make throughout your supply chain and how they impact supply chain goals and objectives, as well as your broader corporate goals and objectives, and really help you understand the sequence of decisions that you make up and down the supply chain and the enterprise as a whole. Now, we've started to conduct these product webinars, again, to give you a sense of what we have been developing that can help you with building more resilient supply chains. And we had our first webinar earlier this year where we did a lot to introduce what we've been building around composability. We have introduced our decision engineering and orchestration platform, which is composed of many different components and services that will be able to all come together to help with creating environments to support your decision making. So rather than having to either rip and replace what one may already have for a technology stack, we are providing capability where you can make incremental improvements using the right solvers, tools, mathematical techniques in a composable way to recompose decisions as needed. So as we think about what we're going to share today, first, we're going to introduce the concept of what we call decision engineering to you. Then I'm going to be joined by a couple of my colleagues here at Gains who will talk through some of the new innovation that we have developed for our customers. My colleague, Jeff Matursky, who is our Vice President of Solution Strategy, will talk through some of the new development to support some of the network design capabilities that we have through risk-adjusted design and discrete event simulation. Then my colleague, Aurelia Sudhiharjo, will talk through and share with you our new capability around demand prediction. And then I'll come back and share with you what we have around this product that we call Gains Connect, which is intended to improve integration between Gains and other systems in your technology stack. Once we go through the innovations, we'll share some opportunities to learn more about Gains, and then we'll leave with a Q&A section. So as we're going through the webinar and you have any questions about anything that you see, please add those questions to the chat and we can answer them towards the end of the session today. First thing I want to share with you are the decision engineering principles. Because at Gains, we believe that building better supply chains actually starts with improving the quality and confidence of the decisions behind them. So we developed what we call the 7 principles of decision engineering. And these principles are guiding us at Gains in how we build technology and how we support our customers, and also how we think about the evolving role of supply chain platforms to help turn supply chains into value generators. So the core principles are listed here, and I'll go through each of them quickly because I suspect that many of you on the call are seeing these for the first time. So one, supply chains are always changing. So your systems need to adapt just as fast, and that's why we build for flexibility and composability. Second is there's no such thing as a perfect answer. Every decision is a trade-off, and those trade-offs evolve. And good decision-making is iterative. Next, embracing volatility and uncertainty. because uncertainty is part of the job, and we don't hide from the uncertainty. We want to design for it. So risk and variability are built into how we model and solve. Then competing stakeholder interests must be reconciled because decisions affect different people differently. We make it easier to balance competing goals and make the decision process more transparent. Then decisions can and should be engineered and recomposable. So our approach is you should use the right tool for the job. There's no single method that works for every problem. So we support AI, optimization, simulation, and more. And look at all of these different approaches working together. Then harness systems dynamics. So you can think about testing your decisions before you commit, where we're able to simulate real world scenarios to understand what might happen before anything goes live. And lastly, ethical considerations, making sure that we do the right thing. Decisions should consider ethics like labor practices, environmental impact, and sustainability. For the product webinar today, we want to focus on two of these decision engineering principles. One will be principle 2, there are no perfect answers, and decision making is iterative. And 5, using the right solver for the right purpose. I will now introduce my colleague, Jeff Matursky, who will start to share with us the new capability around risk-adjusted design.
Well, thank you very much, Amber. What I'd like to talk to everybody today is two areas inside of the design portion of our solution, Supply Chain Architect, that we've been working on and are ready to bring out to our customer base in the market. The first one I'll talk about is risk-adjusted design, and then the second one I'm going to talk about is discrete event simulation. So these, again, sit inside of the design solution. And the first one, risk-adjusted design, is associated with network optimization. So what is risk-adjusted design? For those of you that have been familiar with doing traditional supply chain design, that's using a technique that's called mixed integer linear programming. So it's an optimization technique that for any given set of inputs, you can find truly the optimal solution that respects, using those inputs, a set of constraints and either minimizes costs or maximizes profit. And the challenge that we've had for the past 30 years in using this technique is that all the inputs are deterministic. So if I want to understand a change in demand or a change in lead time or a change in one of my cost elements, I have to actually run another scenario, another individual run, and then I have to bring all those runs together and assess what are the answers. So if my network is changing based on changes in those inputs, then I can have conflicting designs. I may not get a really super clear answer. And so what we do know is that operationally, supply chains are not deterministic, and they have significant variability. They have variability in demand and costs and lead times and supply. And whether it's performance variability, so a lead time has, a range when I'm actually shipping or bringing product in from one of my suppliers, or it's the future demand scenarios that I'm trying to look at to design my network and the associated policies. So think about likelihood of future demand scenarios, not necessarily variability of the demand itself. And so risk-adjusted design is Gain's solution to evaluate this variability, uncertainty, likelihood of future occurrence, any one of the ways that you may want to think about that in one solve. So instead of having to run multiple solves and stitch them together, I can actually run a single solve. Now, it doesn't mean that there won't be scenarios as well in risk-adjusted design, but I'm going to significantly reduce the number of scenarios that I need. So let's walk through an example. And this is a very simple example of one application area of risk-adjusted design that's associated with demand uncertainty. So imagine that I'm a network, and I'm in a situation where I have run out of capacity. and I have the future demand that I'm trying to accommodate, and I'm trying to understand where in my network should I add capacity to existing locations or expand into future locations. And we're going to do this really simply just by looking at transportation costs inbound to the distribution center and outbound to our customers. Of course, we could be much more complicated on the different costs, right? Different types of constraints, but just for illustration purposes, we're going to make this pretty simple. And so this example of this customer was faced with, as they went through their organization and they were gathering up all the future demand scenarios that are coming in from sales, that are coming in from marketing, from product growth assumptions, they came up with 60 different scenarios that needed to be contemplated. And each one of these scenarios has a different level of growth in different regions of the United States. So there's ranges of growth that are happening in the Northeast, the Central, et cetera, et cetera. And you can see that the most significant growth that this customer is planning for is a doubling of their demand in the Pacific Northwest. In addition to understanding the percentage growths that are happening in each one of these scenarios, there's also a likelihood, right? And so there are the most likely scenarios that can happen here, which just for sake of how these got numbered are 1 in 37 up at the top. And then you can see that they trail off, and they trail off pretty significantly. Now, the question might be, do I really need to consider all of these? The answer is maybe, maybe not. It'd be nice to be able to decide how much, right, of this future likelihood do you want to accommodate? And that's one of the things that risk-adjusted design can help us do. We can truly understand how much what I would say is a future risk of demand occurring. Do I really want to look at the outliers and will they change the story? Or do I want to maybe look at 80 or 90% of the likely demand and see what my solution will be? So in the traditional way, what we would actually do is we would run these 60 scenarios individually inside of our solution, the supply chain architect. And each one of these runs would give us a different answer, or could potentially give us a different answer, I should say. And so in this example, right, 45 of these future demand scenarios actually came up with Dallas and Pittsburgh as the incremental DCs to add into the network. And 15 of them came up with Portland and Pittsburgh. And as you look at this and look across all of the places where we're doubling the Pacific Northwest, you would see that it actually picked Portland. And so if I believe that those are the ones that are really going to happen, should I open Portland? It looks like Pittsburgh was in both of them, so you would think that's a no-brainer. But this is typically what supply chain analysts, right, and strategists are going through is I've run this, but now what do I do? What is my actual recommendation? So typically what we would do is some additional analysis, right? We'd look at these two because we're trying to choose between the two of them and ask some questions about, well, my Dallas Pittsburgh seems to actually have, the lowest variation of cost to serve when I'm looking to serve across all these scenarios. So also imagine that if I implement Dallas and Pittsburgh, right, I still have to serve those 15 scenarios where it wanted to be in Portland, but it's going to cost me more to be in Dallas, right? But how much more is it going to cost me? And so that's kind of this cost exposure that's here out on the end. So it's the cost, you can think about it as the cost of being in the non-optimal solution. And so while Dallas Pittsburgh is great for the 6 of the top 10 most likely, right? The cumulative likelihood of those 45 scenarios is I'm covering 70% of my likely future demand. It is the lowest cost, but I actually have an exposure. If any of those other 15 scenarios materialize, I can actually be 14 to 15% more expensive. And then you go to Portland and Pittsburgh, and you can see it is more expensive. It's only the right answer for 30% of my future, but it only has a 9 to 10% exposure of being wrong. Right. So if I were to go implement Portland, Pittsburgh, because I want to really make sure I can serve the Pacific Northwest effectively, I would be wrong on all the other 45 scenarios between 9 and 10%. It would be that much more expensive. So I'm still in a position where I don't know what to do, right? It's not super clear to me because I haven't said, take advantage of looking across all 60 of these simultaneously. And so that's what risk-adjusted design is all about. And so what's really fascinating about the risk-adjusted design solution for this example is that The answer, when I look at all 60 scenarios, taking the likelihood of each one of them, I don't get Dallas, Pittsburgh. I don't get Portland, Pittsburgh. I get a different answer. I get Dallas and Portland. Now, why? And the reason of why is because it is not the cheapest solution in any one of the individual 60 scenarios. But when you try to maintain serving all of those 60 possible scenarios with their likelihood of occurrence, it actually is the least expensive one. And not only is it the least expensive one, it's lower than either Dallas, Pittsburgh, or Portland, Pittsburgh across all 60. It serves all of my top 10 most likely, right? Of course, because it's the only answer, it's covering 100% of the future uncertainty. It's 3% lower in cost. And the really, really interesting thing, right? I mean, if I haven't said enough interesting things, is that the exposure of being in the wrong answer. So remember, if any one of those 60 individual scenarios materialized, this is not the lowest cost, but it is only 1 to 2% off the lowest cost in any one of them. So by simultaneously looking across all 60 of these scenarios, and of course, you could play with the certain, like the scenarios in RAD would be, well, let me change the probabilities or the likelihood of occurrence. Let me determine what would happen if I don't take on 100% of all the future likelihoods. And then those are the types of scenarios. But in any of those, you still have one answer. So we have found using risk adjusted demand in this example, first of all, a different network than I would have even thought of implemented, and one that actually is lower cost across the likelihoods of these future demand scenarios. So we're looking at this being incredibly powerful as customers start using this. And again, we're starting in two places. So it's not every variable that you could do this with. We're starting with demand. And then I'm going to talk about one of the other areas that we felt was a really solid starting point to begin with, and that's facility availability. So when you think about either designing your networks from scratch, I shouldn't say that, excuse me, not designing your networks from scratch. When you think about, I need to add in capacity inside of a network, or I'm trying to evaluate the implications of an existing network and losing facilities that go down for a variety of reasons. It could be, disruptions that are based on fire. It could be disruptions that are associated with strikes. It could be weather-related events. But I'm trying to understand now, what is my best network in an optimization environment? So instead of just forcing things out, I'm trying to understand if there's a certain likelihood that a facility will be closed, what's the best design that I can have? And so this is an example of a customer that is looking to expand their capability in the southeast portion of the United States. So they're a heavy importer, right? And they're right now considering, does it make sense to have a port in the southeast because they are just flowing in all their product on the West Coast. So bringing it in through the southeast and having a location in the southeast from a distribution center perspective. And so in this first table, what you can see here is we've got several candidates. We're contemplating being in Atlanta, we're contemplating being in Savannah, and we're contemplating being in Nashville, right? And I have these customers here of Charlotte, Jacksonville, Birmingham, et cetera. And there's a 35% likelihood that I'm starting with as my assumption for this scenario that Savannah would actually close. So before I take that in, right, these are my costs to serve, right, from each one of these DCs to each one of my customers, right? And if you look at this individually, right, the best single location just based on this alone is Savannah at $340 cumulative, or you could call this 340 million, excuse me. If I say I'd like to try to find if there's a better answer and I'm willing to open up two locations, then you can kind of see the combinations here. And this is deterministic. I've not taken into account the impact to me if Savannah would actually close with a 35% likelihood. So in this example, it makes sense to open up Atlanta and Savannah, right? And you can see that I've reduced the cost by $40 million by opening up two of these locations. Now, the other piece of information that's valuable as I now go into risk-adjusted design is I need to understand that if I decide that what I'm going to do is open up Atlanta and Savannah, and I need in an emergency situation to go use my alternative locations of Atlanta, or should I really be in the network with Nashville to start with? I have a premium cost for emergency space and handling. So I'm not designing Atlanta to have incremental capacity to handle this closure in this example, and Nashville may not have even been in the mix. So if I run this now with a 35% likelihood of Savannah closing, the actual best solution now is Atlanta and Nashville. It is not worth me at 380 million. Now, it's definitely going to cost me more than the deterministic solution of Atlanta and Savannah because I factored in the fact that there's a likelihood that Savannah will close and I will lose its operations and I will have to pay for emergency space and handling somewhere in the network. And if that's the case with these cost structures that have been provided, where I want to actually be is in Atlanta and Nashville. Now, you can see that it's close to Atlanta and Savannah. And so the next likely thing that one might ask is, well, where's the tipping point? Right? What the scenarios in this type of setting where I'm trying to understand what's going on is I may want to factor in now if what if it's not 35%? Clearly, if it's more than 35%, right? If it's greater likelihood that I'm going to lose Savannah, Atlanta and Nashville becomes better and better looking. But what if I flip the other way? What if the likelihood of closure goes down? And so you can actually use risk adjusted design to understand where is the actual tipping point. So at a 31% likelihood, right? We went from 35% to start with to now 31%, right? Atlanta and Nashville is now at a tie with originally Atlanta and Savannah. So what do you learn from this? What you can learn is if I believe that the likelihood that I'm going to lose the Savannah operation, given the cost I started with, and of course you could run scenarios inside of this changing the cost, just basic cost sensitivity. Does that have an impact on this? But if I think that I'm going to have less than a 31% likelihood of Savannah going down, then I would be in Atlanta and Savannah. If I thought I was at anywhere from 31 above, right, I would then be in my Atlanta, Nashville. So these are ways in which, we have envisioned and we have been using and playing around with and dealing with some internal customer or external customers on two application areas. As we keep on growing this out, we will be adding other types of variables into the mix that you can do the probabilities and likelihoods on, but this is where we're starting from right now. So hopefully you can see that there's some really tremendous value that can be gained by putting this into the mix using risk-adjusted design to do your supply chain design and policy development. I'm going to switch gears now and get into discrete event simulation. So discrete event simulation, from my perspective, is probably one of the most underused techniques that we've had at our disposal to do supply chain design policy work under the banner of operational feasibility, right? So let's talk about how we can use discrete event simulation as a complement to the other optimization technologies that we have inside of supply chain architect right now. So again, supply chain simulation will span our entire portfolio of solutions across design, demand, inventory, and supply over time. It is part of our future roadmap to keep on expanding the use cases and the application areas of supply chain simulation. But for right now, we're going to focus in on, and we started with our MVP of simulation to support design work. And so how do I think about the difference between these two and using them? So think about optimization is a technique that helps us determine the structure and the policies. It is prescriptive in nature, right? Given a set of inputs, right? Given a set of choices, inside of that choice, it will recommend in any given scenario exactly what the network structure should be. In a distribution world, it's how many facilities, their capacities, the product to stock at them, and the flow paths through the network from suppliers into distribution centers, and then ultimately out to customers, whatever customers are. And your end customer could be a store, could be a consumer that consumer that's buying from you in the e-commerce world. But I am prescribing what to do. Simulation then tests the performance of that policy and network structure, right, under operational real world conditions and the planning logic that would be used to run that network day in and day out. So typically when we do optimization work, we are not in the network design space, you are usually not doing things lower than monthly, occasionally weekly periods of demand, right? Most people are doing annual models. They could be doing multiple annual models out in the future, but you are not getting down to the fidelity of day by day, right? One might argue eventually you might even think you need to get to hour by hour, but right now we're sitting with day by day. So imagine if you could have your network design be stress tested. Imagine if you can understand how will this thing perform if I run this day in and day out with actual orders, either my historical orders, my customer historical orders, or a projected order stream. I can get an understanding day by day of how the network will fill customer orders. I will actually get a solid understanding of my service levels that I cannot get in network optimization. Network optimization doesn't deal with order level information. It aggregates up all the demand by the SKU or the product group to that bucket of annual or monthly, right? In the occasional weekly. But that doesn't really give me any confidence of how the network's going to run. I don't really know how my daily capacity is going to handle. I don't see literal shipments flowing through the network. And so the value of simulation is to understand performance of the network, true shipments that are being built in mode selection, and an understanding of the customer service levels at an order level, so on time in full, both for orders and for individual line items of this network. And so let's dive into this a little bit deeper, right? The inputs, many of the inputs are coming over from your network optimization model, or it's the existing structure that you have, right? And or it's coming over from what you've done in inventory optimization, or just your inventory policies that you have. So how do I replenish, right? My distribution centers, what are the policies that trigger an order out to my suppliers? And then daily customer orders. Now, many times, right, people have thought this is so hard to use and it's so much more incremental data that I need to capture. And it's really not the case. So, for those that have done network optimization, you're usually collecting the daily customer order history, right? That hit shipment history, customer demand history, and you're using that to aggregate and roll up your data for the inputs that are driving your network optimization. But those inputs are now fed into a discrete event simulation engine, and Gaines has built his own. So there are other commercial discrete event simulation engines that are available. We wanted to have complete control, complete flexibility to be able to modify the components at any point in time going forward. So we have built our own discrete event simulation engine. And basically, you can think about this as receiving customer orders, fulfilling customer orders, shipping customer orders, replenishing stock as needed, then receiving those inbound shipments and stocking new inventory. And so it probably may be obvious to you here that we're not talking about manufacturing, right? We're not talking about any type of product transformation. And intentionally, that's where we started. So we started this journey with focusing on distribution networks, right? It could be finished parts, it could be MRO, it could be raw materials that are coming in, but we're not doing manufacturing and transformation. And then what do you get on the system performance side is that you get this very robust, detailed understanding of customer order fill rates. You now get the daily understanding of the costs that are associated with executing this. You get a working capital view of your inventory day by day of what's sitting inside of my distribution network, as well as what's in transit inbound. And then I'm actually looking at daily capacity utilizations. So now I need to understand, do I have enough capacity in my receiving operations to receive that inbound product or ship that product out to customers? As well as, do I have room to store that product inside my facility? And if I don't, then I can't receive it and it ships out in the yard and it waits for capacity for me to receive it in. If I can't ship it out the door, then that customer order may be late, right? Or I may have to reroute that customer order to another location. And then finally, this is actually designed to order by order, right? It's determining what, if I have available alternative modes of transportation. So let's say I'm thinking about shipping out to my customers and I have truckload and less than truckload. I can have the simulation determine based on a set of predefined rules that make sense. When do I go to truckload? When do I go to LTL? So it's doing building of those shipments and then selecting the mode to go out the door. And so you're providing, kind of getting in a little bit deeper, looking at some of the typical types of outputs, right? You're defining your network. It's not going to tell you what facilities to open. We've done that in network optimization. It's not going to tell you the flow paths of how things are going to move from suppliers to your DCs. It's not going to tell you the assignments. You have predefined everything. Okay. And it's going to then take in that daily order profile of customer demand, and it's going to apply planning logic. And I'm on the next slide going to talk about these various planning logics that are in there that control how supply chains operate, right, day in and day out. But it is then clocking forward. The reason it's called discrete event is there's an event that triggers activity. Think about your actual supply chain. An order gets placed on the distribution center. It's an event. What do you need to do? You need to respond to fulfill that order. So there's a set of logic that gets triggered. Your inventory dips below the level where you need to trigger the replenishment. That's an event. So these are all things that you could think about as a calendar that's watching day by day. And when certain actions happen, or events, better word to use, happen, I trigger something to be done. And I'm simulating, right? Words have been used like digital twin. I'm simulating the actual performance of that network under these sets of conditions. So I'm fulfilling and shipping customer orders. I'm placing and receiving replenishment orders from my supplier, right? And I'm restocking and managing the inventory inside of the network. And then I'm looking at all of the key metrics that are happening day by day. And so some of those are shown on the side that you can see daily inventory levels. You can see that by working capital investment. You can see that by whatever is your unit of physical measure. In this example, it's pallets. You can see it by the dollars that are in there. And then I can also understand the utilization. And then on the bottom here is a really powerful way of understanding customer fulfillment, right? I can now understand if I'm allowed to in my network to ship from secondary and tertiary locations. So when an order drops on my primary location, then I've decided based on my policy or network optimization work, if I'm out of inventory, what do I do? What rules would I like to test? Am I allowed to back order, or am I in a fill or kill situation? Am I allowed to route that to another facility? And when I route that to another facility, do I have to route the whole order? If I can't fill it complete, can I route just part of the line? Right? And so when I don't have enough inventory based on whatever these policies are, I can capture my lost sales. So I may not be able to have back order, or maybe I have back orders with limits. You're allowed to hold an order in back order for, let's say, 30 days is your policy. But after 30 days, if I don't fill it, I lose the customer order. And then, of course, we're monitoring on time in full, or OTIF. But what's really, really powerful that I can do inside of simulation that I cannot do inside of the optimization technology is I can apply logic. And one of the biggest logics that I can apply is customer order routing. So this expands our capability to design policies and or test our existing policies on order fulfillment for customers. So it's all those things that I just talked about on the prior slide. Am I allowed to partially fill? So an order comes in, can I partially fill a line? Can I partially fill an order? And if not, what do I do? Can I split a line? So if I have enough inventory for a SKU on my order, I have 80% of it. Can I fill 80% there and send the other 20% somewhere else? Or does that 20% need to be back ordered? Now, let's not get this incorrectly. Simulation is not going to decide for you in a single run what's the best thing to do, but it provides you an environment to test these alternative policies to determine the impact of what would actually make sense. So it's supporting policy development, right? And then again, can orders or lines be back ordered? Buying logic. So we think about buying product, right, that's being triggered by inventory. So as inventory dips below whatever my policies are that I've developed, whether it's min max or SS or RQ, I am now going to pull the trigger. But when I pull that trigger, like how complicated is my logic? Do I order one SKU at a time? Do I go out and look across other SKUs that haven't hit their trigger, but maybe they make sense to order right now? Do I want to actually try to build up my order so that I'm thinking about transportation economics, like filling up an ocean container to a certain level of utilization? Am I allowed to transfer from other locations? Can I go and look at inventory in other locations and see if they're in excess and pull it into my primary location? So it's controlling how inventory will be replenished inside of the network. Receiving operations, what's my logic there? So how do I actually model? Am I allowed to, do I have unlimited capacity? Do I have a certain amount of product that I can receive each and every day? If I can't receive it each day, what happens? Does it go into an offsite 3PL and then I have to go pull it there when I need it? Or does it get held in the yard on the trailers or containers that it came in? And once I have capacity to receive it, or storage capacity, which is not highlighted here, right? I might be able to bring it in, but I've got no place to put it in my facility, so I've got to still hold it out until I'm ready to go. And so what you'll see when you use this is that you actually get a very clear understanding of, do I really have enough capacity? While I might have come out of my network optimization models and thinking that I'm good at an annual level based on the average assumptions I made, or at a monthly level, I can now see day by day based on how orders are flowing that I have to ship or receive. Do I have that capacity and do I have a place to store the inventory where I'm bringing it in? And then finally, the last one is transportation mode selection, which I talked about before, where we're queuing up, we're determining what's the latest that I can ship out of this facility to actually meet my obligation of a customer due date. So I'm waiting and waiting for as long as I possibly can. I'm building up as much as I can inside that order. I'm determining the triggers if I'm allowed to go to secondary locations because I can split, right? When do I need to ship that off to that secondary location? And then based on the size of the load that's being created at the location that's shipping, I will make a selection between truckload and LTL. So that's a preview of simulation. I would tell you from my experience of doing this work over the past 30 years, I really wish I would have used this much more. We most recently have come through a full-blown engagement with one of the Gains customers that is designing their supply chain, that is using network optimization, inventory optimization, and simulation. And the level of buy-in, the level of confidence in the policies that were created, the tweaking of receiving capacity was invaluable. They would have never gotten to the same place unless we actually incorporated in simulation. So thank you for the opportunity to bring these two new exciting developments in the supply chain design space to you. And with that, I'll turn it over to Aurelia to talk about demand prediction.
Thank you. And over the next several minutes, we'll discuss the challenge of traditional forecasting, the cost of it, and how demand prediction fits in all of this. As we extend our catalog of individual components, this is just another step of our composable strategy where you can subscribe to an individual component without that big rip and replace method. Demand prediction is one of Gain's newest individual component product offering within the demand planning family. Most forecasting today is backward looking. It's built solely on past demand data, but past demand is a lagging indicator. That means that it tells you what happened yesterday and not what's on the horizon. This means that there's no insight into tomorrow's economic shift or the next shock to your marketplace or sudden market pivots until it's already too late. Result, planners spend half their time firefighting exceptions by manually adjusting forecasts last minute instead of proactively shaping supply strategies. And that's the hidden drag on your operations. So, reactive planning isn't just inconvenient, it's also expensive. Stock out means missed sales and unhappy customers, while excess inventory ties up your cash. You may have forecast accuracy isn't everything, but here we think that it is one measure of success that has a large downstream effect, a critical leading indicator for everything downstream. That means it's a indicator for setting your safety stock levels, timing replenishment order, and optimizing inventory investment. At the end of the day, your inventory is one of your biggest assets, and our job is to maximize its return. So, by improving forecast accuracy, you're unlocking a better ROI on that asset across planning, replenishment, and finance. When you improve accuracy, you order at the right time and in the right quantities, and as a result, free up capital for other projects. Even a 5 percentage point gain in MAPE can translate into hundreds of thousands or even millions saved or earned each year. Now that we've seen the real cost of inaction, let's focus on outcomes. We ran benchmarks at three gains customers, each with very different profiles. First, Company A is a 1.5 billion industrial automation manufacturer. Company B is a $410 million jewelry catalog retailer. And the third company, Company C, is a 11 billion electrical distribution enterprise. After running demand prediction on three of these companies, each has a consistent 20 to 30% improvement in forecast accuracy. And these are the kinds of results that translates directly into better inventory planning, more precise replenishment, and a stronger ROI on your inventory assets. At a high level, here's the heart of demand prediction, which transforms your data chaos into confident, forward-looking forecasts in 5 different stages. First, we ingest. We connect directly to your systems and automatically pull historical demand transactions and material data. So no manual exports, whether you're already a gains customer or not. Second step, enrich. We don't just feed raw demand history and material data into our model. We generate a curated engineered features. Then, as an option, we can layer in curated lists of exogenous data like price index, macro trends, maybe promotions, and so on. For a simple example, for a jewelry manufacturer, we might pull in daily gold price data. So during the model training, the model sees that when gold prices drop, sales historically spike. It learns to assign a high weight to that gold price feature. Then, next month, if gold falls 5%, the model automatically boosts its forecast, anticipating that same jump in orders. That additional context is beyond what the traditional ERP and traditional forecasting method can tell you. Third, we predict. We build a bespoke model for each client by using an iterative ensemble learning method, trained on your enriched dataset to capture your unique demand patterns and generate highly accurate monthly SKU location level predictions. Next, we deploy and monitor. Predictions are pushed via API models. So models are also retrained monthly on a rolling window, and we monitor accuracy with RMSE metrics, reported in both aggregate level and segmented by plan period and forecast horizon. And lastly, it's composable. As an API first solution, demand prediction works together and plugs easily with Gains demand forecasting, whether it's Gains X, version 9, as well as any other forecasting platform without that disruptive rip and replace. This is just a preview of the demand prediction service UI with the new Gains look and feel. Firstly, here's the landing page where users can navigate to the training or predictions page. Next, this is how you can see what your SKU location prediction is and navigate to understanding what features most impacting the SKU location prediction for this month output. Here is where you can see what features are most impacting your SKU location outputs. And the point of this slide is to show behind the scenes or through the looking glass, so you can build confidence in this model as well. And finally, if you are a gains demand forecasting user, you can enable to see the predictions in your demand forecasting screen. At its core, demand prediction transform your planning from a rear view exercise of what happened into a forward looking strategy of what's coming. That shift matters because it means you're no longer scrambling to fix yesterday's problem, but instead, you're anticipating demand changes before they happen. It enables you to, one, stay ahead of disruptions like market shifts or promo different spikes rather than reacting after the fact. Second, optimizing your resources. By aligning your replenishment, production, and inventory with the expected demand, it will reduce your rush cost and overtime as well. Thirdly, improve your overall service levels. By keeping the right products in stock at the right location, it boosts fill rates and customer satisfaction. And finally, freeing up your capital. When you order more precisely, you trim excess inventory and can redeploy that working capital. Finally, because we're API first and truly composable, we slide seamlessly next to Gains demand forecasting, whether X or version 9 or any other forecasting platform. There's no big effort of that rip and replace, just true plug and play. Demand prediction also doesn't replace your existing gains forecasts, it elevates them. By intelligently using gains forecast models as a feature and identifying each SKU location to whichever method, traditional or machine learning, delivers the lowest error to your population of SKU location forecast. In short, by looking forward into a competitive advantage, you gain true foresight, boost accuracy across your entire catalog, and build a resilient forecast plan that anticipates shocks and driving measurable ROI on your biggest asset, your inventory. Thank you, and that's all from me.